All right. Wire gauge is going to be our next thing. We went through it before. So typically we're going to either see a number 6 feeder coming in there. That's going to be for 60 amps. A number 2 aluminum or a number 3 copper. And these do need to be committed to memory. Those are what we're going to see for 100 amps. And then we're going to be dealing with 2-aught copper, most likely for 200 amps where it comes into it. And that's what they're showing here. So I know it says number 4. That is what the NEC calls for. But very common in the Chicagoland area, we're going to see number 3 coppers. Wires at the service mast need to be the same as what's in the panel. We run into this quite a bit. You're going to see that the mast that comes down there all of a sudden might be a number 6 wire, or even the service drop coming across the top could be a number 6 wire. And then as it comes inside, it's either bigger or smaller. So somebody got into the meter and changed things out. We want to make sure those wires are the same size. And at least, you know, we should be suspicious when things are changed. I also like to look at that tag on the meter panel. And it's a tamper tag. If I see that that's cut or broken in any which way, then I know that somebody was in there doing some sort of work. In our area, the electric company is the authority having jurisdiction. They're the ones that can approve or disapprove any sort of hookup where it comes to it. So if they want to have smaller wires that are feeding their system, they could do whatever they want to do. You know, they're the authority having jurisdiction. But for me and for our company, we don't want to take ownership of issues. So if we see something that's out of the norm, we're going to document it, plain and simple. Meter panels are not supposed to have anything coming off of them. All right. So if we do see an outlet or something in here, we don't know if it's before the meter or after the meter, but either way, we're not supposed to be using the meter panel as a junction box, and so we can't run wires through it, so we shouldn't see any taps coming off of it either. This one I just thought was pretty cool. They could have advertised that free air conditioning was being given. So if you look at the meter in the upper right corner and we follow that pipe coming down, we see that it goes to the disconnect for the air conditioning. We go to our seal tight and that feeds there. Now if this was all done before the meter, that wattage that's being used for that air conditioner is not going through the meter, hence that meter's not going to end up being reading any sort of electricity that's going to be done through the air conditioning unit. We do have to do a little bit of writing here. If we have an overhead service drop, then we need to know what our clearances are. So these do need to be memorized, all right? Roadways, 18 feet. I'm more worried about the NEC. ComEd is for my local jurisdiction. They do allow less, but we don't see too much of that. All right. So roadways, 18 feet. Residential driveway, 12 feet. I would like you to still know driveways that are designed for farm equipment. That's actually 15 feet. So 18 for roadways, 15 for farm equipment, 12 for residential driveways, pedestrian, or any place that I could walk underneath those wires, whether it's a deck, lawn, sidewalk, whatever, 10-foot clearance from that. Windows, doors, porches, etc., that's 3 feet, and that's mostly horizontal and below. All right, so as I measure that, that's going to be, if I'm standing in front of a window and I'm looking out, so we're going to go from the one side to the front, to the other side, to down below us. That's all 3 feet. 5 feet for the local electric company here in Chicago, but 3 feet for the NEC. That doesn't include above, all right? I could be right above the window. I can't be in front of the window, but I can actually be right above it when it comes to it. Other things that come into play is over roofs. Let's see if that's here. It is here. Good. When we're dealing with over roofs, if it's a sloped roof, and a sloped roof is anything over 212, all right? Anything under 212 is going to be considered a flat roof. We have two numbers that we have to memorize for this. It's 18 inches and 3 feet. And it all depends on the horizontal run. All right. So what we're saying in this drawing is that from that service mast till it gets to the overhang, that has to be less than 4 feet. If it's less than 4 feet, then I could be within 18 inches of the roof. And we're talking about the lowest point. So here we see that there's a splice that's pretty much our lowest point on there. Maybe it's right at the gutter line, but that lowest point has to be at least 18 inches off the ground. Now, if that horizontal run is greater than 4 feet, then that changes to be a 3-foot clearance to that roof line. These are our windows again. Again, 3 feet, right, left, front, below. And it's just the wires. We're not talking about the mast or the pipe that we see. We're talking about just the wires themselves, all right? So where that drip loop is coming into play, because that's less than 3 feet from that window, that's something we should be calling out for clearance issues. Clearance issues also come into play at the panel down in the basement. We need to have enough room to where the electrician or who's ever going to be working on this panel that they could work on it safely. All right. So there can't be anything that's going to trap them into this little area, and it needs to be wide enough so they could get in there and work. So if you're going to be memorizing numbers, 30 inches width, and it's not 30 inches from the center or from the left and the right, it's just 30 inches total of working room in front of it. So if this thing's off in a corner, kind of on one side, but I still have a good 30 inches or more workspace to it, that's okay. Behind the panel is 36 inches. If I have to crawl into a tub or I got a post or something that's supporting things, then that comes into play as well. The height of the panel is typically 6.5 inches. The area above the panel is kind of a safety zone for the electric. There really shouldn't be anything that goes up there above it. We want to let more conduit or anything that's going to expand on the system. We want to give them easy access. I mean, I don't have it in me to tell somebody to go ahead and move that waistline that's above it, but it would have to get me to start thinking. If I thought that it was put there originally, I would probably be less inclined to say something about it. If I thought that it was a rehab and it was added, then I think I'd be a little more inclined to say something about it. So again, no foreign objects are above that panel. It's a dedicated space. One thing that Corey put in here for me, which I'm thankful for, is he cited the actual codes in the NAC where it's in there. So if you want to verify this, that's where you would find it. The maximum height of the breaker is 6'7". Usually they're going to be around eye level is what I like to see. Common sense here. We got the electrical panel behind the water heater. There's really no way of anybody to get in there and do any sort of work. Stuff like that is kind of a no-brainer. All right. So this is a little bit of review of what we saw before. We're still going to refer to these as a single-phase system. Again, we're only going to be counting the wires that come in there. Now, this picture throws a little bit of a curveball because one of those wires that we're seeing is the grounding electrode conductor. And on the left side, there's a bus bar, and that's attached to the back of the panel. And that's where my grounding electrode conductor is attached to. All right, so we're not going to count that wire when it comes into it, but we are going to count the other three. Neutral, hot, hot. One of the other things, too, when you open up the door to the panel, if you see two breakers tied together, so a 240 breaker, then that's another good clue that you have a single-phase 120-240 system. If you open up that door and you see three breakers tied together, and this is going to be either on condo buildings or big, large homes, and those are three-phase systems. We're going to stay out of those. They can start creating arc blast that gets really dangerous. It's going to be over all of our heads. I'm going to ask that you refer them off to an electrician and just say you don't know. So don't take the cover panels off unless you know what you're doing on those. Again, you're going to have three energized conductors. The easiest, quickest clue that you're going to end up seeing those are going to be 3 breakers all tied together when it comes to it. So typically, again, they're going to be on either commercial buildings or very large residential buildings that comes to it. So we mentioned before about measuring between the hot and the neutral, 120. We measure between the hot and the hot. That's where we get our 240 comes in there. So this is our typical sine wave. And the way this works is I'm going to have a magnet that's going to take a coil. One side of the magnet will be positive, the other side of the magnet will be negative. And each time that goes around, that coil is going to create a positive charge, a negative charge, positive charge, negative charge. In which case it's going to create positive voltage, negative voltage. And that's going to happen 60 times every second that it's going to revolve around there. Hence we get the 60-second cycle. Now with a 120, and that was a 120 sine wave that came in there. That was one cycle that you saw. When we're dealing with a 240 cycle, it's basically the same thing, but both of those wires are completely out of phase of each other. So in this case, the blue wire would be the same one we saw before, where the red wire would be the opposite as it comes in there. But you can see when one is positive 120, the other one's negative 120, and then they switch places. The difference between the two of them, maxed out, is going to be 240 volts. Now the electrical panel, talk about clearances, and these are meant to be a little bit humorous, but you're going to run into them. When people finish their basements, if they want to have a bathroom or a shower and that electrical panel is there, then I guess they're going to put the panel in shower and everything right where the panel is. I mean, it doesn't take a rocket scientist here to determine that that's just not a smart move, all right? And granted, we don't want to let any water get in there. That's true. But more realistic, I mean, just putting the plastic over it isn't really going to protect anything. It's the humidity. So if that humidity starts getting into that panel, that humidity causes things to rust. Rust is resistance. Resistance creates heat. And that's when we start getting into problems with our electrical panel. All right. So here we lifted it up. It's just not a smart idea. I do want to show you what aluminum wire looks like, more specifically solid aluminum. These are the neutral conductors that are coming back, and they're on the neutral bus bar. But you can see that we have plastic insulation. You can see how silver and shiny everything looks in these diagrams or these pictures. And again, this is a mandatory defect. Solid aluminum branch circuits, we do have to report the presence of that. And that's per the state of Illinois SOP. CUAL, COALR, those are all different ways to determine whether or not the appliance or the breaker or the switch or the outlet is able to take copper or aluminum or both. All right. And so if you see COCU, that stands for copper. AL, ALR, that stands for aluminum. If you start seeing a do not enter sign on these things, then that's going to be a problem. So this slide here talks again about the solid aluminum branch circuit. All right, so if it's stranded, it's okay. If it's a service wire or feeder wire, that's okay. Doorbell, other transformers, those are typically stranded. That's going to be okay. Aluminum wire will be in plastic and not in cloth. Even though I still think tin-clad copper is just ridiculously old and it gets dried out and brittle, that's just my opinion on it. It's not a mandatory defect. So we don't have to call that out. That's going to be focused more on your opinion. I mentioned earlier when we were writing some things down that aluminum, solid aluminum branch circuit was used from the mid-60s to the mid-70s. The aluminum wire industry is actually making a push to put their wires back into residential electric. There's solid wires back in here. They say that they've remixed the aluminum and redid it so it doesn't have that aluminum creep and that different sizing stuff that comes in there. And they feel that it's safer. They're still requiring that things have to be torqued because obviously they don't want to take responsibility to stuff. And because nobody's ever going to be torquing and tightening screws and wires. So far, the code officials are just fighting it. And they're pretty much not allowing it to come in there. So I don't think it's written into our codes at all, where it's allowed to come into it, but I do know that the aluminum industry or the wire industry is making a push for that as well. So aluminum wire is considered an increased fire hazard, plain and simple. We're going to go through a lot of these terms as well. We're going to hit that grounding and bonding again as we go through these things and get a few different definitions in here.